Hello, class. So on Wednesday, we left off with this particular example from section 1.2. So this was example 6. We finished everything else in that section. So I figured I'd just make a video to explain this particular problem to you all. All right, so this is still applications of applications of linear equations. This particular problem is about healthcare expenditures. So the problem reads, the projected per capita healthcare expenditures in the United States where Y is in dollars. Now that's pretty important. Let us know what Y, or the dependent variable, is representing. Where Y is in dollars and X is years after 2000. So it seems that our independent variable is a time component. But this time component is, when X is equal to 0, that's going to be in, that means we're talking about year, 2000. And when like X equals 1, then we mean like 2001 and, so on. So just keep that in mind with this problem. All right, so the per capita healthcare expenditures in the United States where Y is in dollars and X is years after 2000 are given by the linear equation. Now, this is a model. Now, what models can do for you is they can help you predict different values, different rates, things like that in the future. Or they can also kind of help you see what happened in the past as well. So let's see what our first sort of task is. We're using this model and how the parameters are set up. It says, what are the per capita health expenditures in the year 2018? All right, so we talk about years, right? That means we must be dealing with X. Now, keeping in mind that when X is equal to 0, we're talking about the year 2000. So for us, when X is equal, or rather, when the year, let me switch this up. When the year is 2018, what that tells us is that X equals 18. All right, so if X equals 18 and we have this model here, then we need to do some substitution. So let me write our model down here. Y equals 416x plus 8042. And we're just going to substitute in X equals 18. And I should probably do that in a different color, right? Just to show you. We're going to substitute in X equals 18 into our model. So we have Y equals 416. And I like to do open parentheses, sets of parentheses, whenever I'm substituting values in. This just kind of helps me keep track of everything for the work that I'm doing. So let's bring up our handy dandy calculator. 416 times 18 plus 8042. I end up with the healthcare expenditures in the year 2018 being 15,030 per capita. All right, so this is in the year 2018. It kind of just shows you a little bit how dated this might be, but it's all good. So pretty much, thus far, it's been a lesson on how to substitute in different values of the independent variable and find the resulting dependent variable's value at that point. Since there are two parameters, we're able to substitute in for both X and Y depending on what the problem gives us. And we'll see that in the very next part of this problem. So the very next part of this problem says, if this model continues to describe healthcare expenditures, when will the per capita expenditures reach $13,000? All right, so we're looking for when expenditures reach a certain amount of money. Now let's go back to the way we defined X and Y. Notice it says Y is in dollars. All right, so Y is in dollars and X is years. So we don't describe, well, I guess you could describe time as money in a way, but we don't assign typically a numerical or a monetary amount to describe the amount of time that, it's going to take. Like how long is it going to take you to drive to whatever, and I say, $82.12 because of how much I make hourly, something like that. So if they give us money, then we're going to be substituting in for the variable that deals with money, which is Y. So we're substituting in this time for the dependent variable. So notice before we substituted in for the X, and X is representative of an independent variable. We're substituting in for Y because Y is a dependent variable. So we're going to take the same model, and the only difference is I'm going to replace Y with 13,000 and set that equal to the right-hand side of the model as we were given. And I probably should just put a little point up here to let you know that's the first part and that this is the second part. All right, so we have the 13,000 there. I just felt like cleaning that up. Now we can get our variable term on one side and our constant term on the other side. So I'm going to subtract 8042 from both sides. And today I just don't feel strong enough to do a bunch of mental math, even though I should. It's all good. Maybe tomorrow. 13,000 minus 8042. I end up with 49.58. Now, I'm going to flip-flop things so that my X term is on the left-hand side and my constant term is on the right-hand side. So I end up with 416X equals 49.58. Now, I'm pretty sure you can already see what's coming. I'm going to divide both sides by 416. So this divided by 416 gives me 11.918. And this is the years, right? So this is years after 2000. So it's almost 12 years after 2000. So it's like, I know it's 2011, but let's try to figure out what month it is. All right, so just on a little bit of nerd science here. I take that decimal, and this is part of a year, right? So if I multiply it by 12, that'll tell me what month it's in. So it's in November. So November 2011. And I could take this further and, multiply the 0.016 by the day. Or there's 30 days in November. So it's the beginning of November type. So it looks like November 2011 is when the healthcare expenditures will reach, when the expenditures will reach 13,000. Well, I hope this helps. Feel free to rewind the video. Feel free to pause the video at any point. Feel free to let me know if you have any questions, and I'll see you all in class next Wednesday. Peace.